Hello, everyone. In this presentation, I'll show that standard learning tasks require interaction in the models of distributed local privacy, of distributed learning with bounded communication, and in the statistical query model. I'm Yuval, and this is a joint work with Vitaly Feldman, and the research was done while at Google Brain. So we'll start by discussing the model of non-interactive local privacy. So here there's a server that wants to compute a function on private data that is held by users. And in order to perform this computation, the server will have to receive some information on the user's data. But the server is not trusted, and every user should only leak minimal information to the server. And for example, you can think of a situation where there is a political candidate that wants to estimate how many people will vote for her in California. But we don't want her to know exactly who supports her. So in order to ensure that this information is not leaked, we can use local privacy. Now, in this paper, we'll focus on learning, where each user holds one pair xy, where x is a feature vector, y is a label, and the goal of the server is to learn a function that maps x to y. And we will assume that the communication is non-interactive, which means that first the server will send requests to all the users, and then each user will send back a response. Now, this response is a message that, on one hand, it depends on the input of the user, but it will only leak little information about this input. And formally, for any two different inputs of a user, and any possible message that this user can send, the ratio between the probability to send this message given one input and the probability to send it given the other input, this ratio is bounded by e to the power of epsilon, where epsilon is a parameter that will be constant in this talk. So next, we would like to distinguish between interactive and non-interactive communication. So as we discussed, in the non-interactive setting, there is one round of requests and one round of responses. And we can compare this to the interactive model of communication, where there are many rounds of communication. Now, this latter model is stronger, but interactive protocols will take longer because of network latencies. And therefore, most of the deployed systems use non-interactive communication. Now we'll move to the main results. And here we show that interaction is in fact necessary in basic learning models if the number of samples is sub-exponential. In particular, this will hold for stochastic convex optimization of linear models and for linear classification with a large margin. And don't worry, because I will define these tasks later. And we can compare this with the interactive model, where these tasks can be solved efficiently. Now, in terms of prior work, the first to show a separation between interactivity and non-interactivity in private learning were Vitaly et al. And they used a synthetic class of functions. And there are also lower bounds related to convex optimization and linear classification that we will discuss in depth later. So now I'll mention also the results on learning with communication constraints. So here we have a similar non-interactive setting, but instead of enforcing privacy, we will just limit the number of bits that each user can send. And for this model, we show that the same learning tasks that we discussed in the previous slide require each user to send a polynomial number of bits if the number of users is sub-exponential. And we can compare it with the interactive model, where it suffices just to send 1 bit per user. And the proofs, both for privacy and for communication, follow from a lower bound on statistical queries, which is a different model. And the reductions were proven in prior work. Okay, so next I will discuss stochastic convex optimization, then linear classification, and I will focus there on local privacy. And then I'll move to the proof ideas and end with a summary. Okay, so let's start by discussing stochastic convex optimization of linear models. So here each user receives an IID sample from a distribution D over pairs XY, where X is a D-dimensional real vector, Y is a real number, and the goal of the algorithm is to learn a function that maps X to Y. And we think of each linear function as an inner product of X with some vector W. And the goal is to learn W. Now, in order to quantify how good is each choice of W, there is a loss function, L, that receives both the inner product between W and X, which is the prediction, and the true value of Y, and it outputs a penalty cost. Now, we will assume that this function is both convex and Lipschitz, and for example, you can think of the squared loss. Now, finally, the goal of the algorithm is to find some vector W that minimizes the expected loss with respect to a random XY pair that is drawn from the distribution D. Okay, so now let's move to discussing prior work, and most of it corresponds to general stochastic convex optimization rather than linear models. So here, in the interactive setting, polynomial time algorithms are known, but non-interactively, the best known algorithms require exponential sample size. And in fact, Smith, Takuta, and Upadhyay showed that any gradient or Hessian-based algorithm cannot learn non-interactively with a polynomial sample size. And it was later generalized by subsequent prior work. But these bounds didn't hold against any algorithm, and it remained open whether there exists efficient non-interactive algorithms. And before moving to the result of this paper, I would like to add 2 things about the prior work. So first of all, these lower bounds hold against algorithms with a few rounds of interaction rather than just 1 round. And secondly, that there are fundamental learning tasks that can be performed efficiently non-interactively, such as least squares and principal component analysis. Okay, and in this paper, we show that any non-interactive algorithm requires an exponential sample size. And formally, there is a standard convex one Lipschitz loss function L, such that any non-interactive algorithm requires a number of samples that is exponential, either in the dimension or in the approximation error alpha, where we define alpha as the difference between the loss of the algorithm and the minimal loss that is achieved by the best choice of W. And I will add that the exponential dependence in the minimum of D in 1 over alpha is tight for linear models. And for general convex optimization, the sample complexity should be exponential, even for constant alpha. So now we'll move from convex optimization to linear classification. And in fact, the bound on optimization follows from the bound on classification. So we have a similar setting, but now we will learn a binary classifier rather than a real valued function. And we will assume that the support of the distribution D is linearly separable, which means that there is a hyperplane that separates between the points labeled as 1 and the points labeled as -1, as you can see in the plot. And the goal is to find a classifier that classifies correctly nearly all the points drawn from the distribution D. And I would also like to introduce the margin gamma with respect to the distribution. And this is a quantity between 0 and 1 that quantifies the linear gap between the points that are labeled by 1 and the points that are labeled by -1. And it will be easier to learn when gamma is larger. Okay, so let's discuss the related prior work. So Daniely and Feldman showed that non-interactively, the sample complexity is at least polynomial in 1 over the margin, while the upper bound is exponential, and this leaves an exponential gap. And for interactive algorithm, there exists an interactive algorithm with a sample complexity that is polynomial in the minimum of the dimension and the margin, and 1 over the margin. And this already suffices to give an exponential separation between interactive and non-interactive when the margin is exponentially small. But the question that one would ask is what happens when the margin is large. And in this paper, we show that even in this setting, exponential sample is unavoidable. And formally, for any non-interactive algorithm, one requires a sample that is exponential either in the dimension or in 1 over the margin. And this will actually hold for any algorithm that is slightly better than a random guess. And also, there's a nearly tight upper bound. Okay, so before moving to the proof, I'd just like to say that there are other models of interactivity and interesting separations between them. Okay, so now we'll move to discuss the proof that uses statistical queries, simple Boolean analysis, and moment matching. And these techniques were also used by prior work to derive lower bounds. And I'll start by discussing the statistical query model. So here, instead of getting samples from the distribution D, we will learn from queries on the distribution. And how does this work? The algorithm can submit any bounded function, h of xy, as a query, and it will receive the expectation of this function on a random input that is drawn from D, together with some small added noise. And for example, you can get the fraction of points that are labeled by 1 if you'll query the function h of xy equals y. And similarly, you can get all the moments of the distribution approximately using statistical queries. And in fact, you can implement gradient descent and most learning algorithms using statistical queries, although this model is generally weaker than the standard learning model. And the concept of non-interactivity can also be defined in the statistical query model. And here the algorithm will have to submit all the queries at the same time. And once they are answered, it cannot ask any more queries. Okay, so in this paper, we will just prove a lower bound on linear classification with statistical queries. And all the other results will already follow from known reductions. Now, the reduction between statistical queries and local privacy was given by Kathivitwan-Tan et al. And the first reduction for limited communication was given by Ben David and Dichterman. Okay, so now let's move to discuss the proof details on the statistical query lower bound for linear classification. And it relies on finding two distributions over pairs xy that satisfy two important properties. So on one hand, these distributions disagree on most of the classifications, as you can see in the plot. So the blue distribution classified as +1 points that are classified as -1 by the orange distribution, and vice versa. And the second property is that it's hard to distinguish between these two distributions, and which means that they will nearly match all the moments. And in particular, for any monomial on x and y, the expectation of this monomial with respect to the first distribution is very close to the expectation with respect to the second distribution. Now, using this indistinguishability property, we can construct a hard class of distributions if we take all the distributions that are obtained from these two distributions by flipping a subset of the coordinates. And this class will require an exponential number of statistical queries if we want to learn it non-interactively. And the proof will use simple identities in Boolean analysis. And now we'll describe how this pair of indistinguishable distribution is constructed. Okay, so we'll start by finding two distributions over the real numbers that have two properties that are similar to the previous two properties. So first, their support is near the disjoint. And as you can see, the blue distribution is supported on points greater than gamma, while the orange distribution has most of its mass on points less than minus gamma. And secondly, these two distributions match all their low degree moments and nearly match the high degree moments. And in order to find them, we will apply a theorem from what is called the classical moment problem. And this relies on finding orthogonal polynomials. And I just wanted to say that in order to give some buzzwords, but I'll skip the details here. Okay, and next we will lift the two distributions over the reals into distributions over the hypercube, obtaining two distributions with the following properties. So first, they have nearly disjoint support. As you can see, the blue distribution is supported on points that are right of the hyperplane on the right, drawn on the right, while the orange distribution is nearly supported on points left of this hyperplane. And in particular, the blue points will have the average of their coordinates at least gamma, while the orange points will have the average at most minus gamma. And the second property is indistinguishability. And this means that this distribution will nearly match their monomial moments. Now, let me explain how the blue distribution is defined. So in order to sample a point x from this distribution, we will first sample a real number p from the blue distribution of the previous slide. And conditioned on p, we will sample all the binary coordinates of x independently, each of them with mean p. And similarly, we will define the orange hypercube distribution. Now, the two properties of the hypercube distributions will directly follow from the properties of the distributions over R. So we successfully constructed two distributions over the hypercube, but our final goal is to construct distributions over pairs x, y, and this will be obtained by combining multiple copies of these hypercube distributions. And that's what I'm going to say about the proof. Now let's move to the summary. So we showed that standard models of learning require exponential sample size in the non-interactive private setting, while they can be solved efficiently with interaction. And the same proof implies an exponential lower bound on non-interactive statistical queries and a polynomial lower bound on the number of bits that each user had to send in the non-interactive communication model. Now, for the proof techniques, we use moment matching, Fourier analysis, and statistical queries. And finally, with excitement, let's move to the open problems. So first, in terms of the lower bound, it was proved only against one-round algorithms. And even for 2 rounds, it is open whether there exist efficient algorithms. Probably no. And in terms of upper bound, so it will be interesting to find assumptions on the distribution where it's still possible to learn interactively, and also to characterize what optimization tasks can be solved without interaction. Because some tasks are easy to do in one round. And thanks for listening, and I'll see you behind the screen at the conference.